So we will summarize what we have done today. So today we have discussed bandwidth of frequency modulated waveform or frequency modulated signal. So the structure, a typical structure of a FM signal is AC cos 2 pi FCT plus 2 pi KF MU du, where this KF is frequency sensitivity, right? And units is hertz per volt. So if we just represent 2 pi kf with CF, and integral of this message signal with AT, then our frequency modulated signal would become this AC cos 2 pi of CT plus CF AT. We have just replaced 2 pi kf with CF and our integral of message signal with AT. We now define our signal as XPCT, that is a pass band complex signal. So you can write this FM signal like this, real part of XPCT, where XPCT is this AC exponential e to the power j 2 pi FCT plus CFAT. It's very trivial to see that XFMT is nothing but real part of this signal, complex password signal. This you know in your previous from your previous classes. Why do we call it a complex passband signal? So in order to analyze the bandwidth of this modulated frequency modulated signal, we first define a complex passband signal XPCT like this. So our XPCT is AC exponential of j 2 pi FCT plus CFAT. We just write in this form after a small, just after doing the very trivial manipulation, we can just write e to the power XPCT as AC e to the power j CFAT into e to the power j 2 pi FCT. Now we use this expression, that is EX e to the power x can be written as 1 plus x square by factorial 2 plus x cube by factorial 3 and so on. So using this representation of e to the power x, we replace e to the power j c of at with this. So in order to get the expression or this summation series for e to the power j c of at, we have to replace x with j c of at, which is g c sub f. So don't confuse it with the frequency, it is c sub f. So our passband, complex passband signal will be AC 1 plus, we replace x with jc of at. So x square, j square is minus 1, j cube, here it should be factorial 3, factorial and so on. And you have to also multiply it with this. So from this step A to step B is quite clear that we use this equation and we get XPCT in this form. So as we know from our previous discussion that XFMT is nothing but real part of this complex passband signal. So our XFMT is the real part of XPCT. And we write XPCT from this equation. We replace here. So now the other representation of our frequency modulated waveform is this real part of AC plus ACJ C of AT minus ACCF square A square T by factorial 2 and so on. We have taken just three terms, and all other terms are just, there are infinite terms. Sorry. So excuse me for sorry for the inconvenience. So so Now we analyze each term, this XFMT, term by term. So real part of AC into e to the power j 2 pi fct is AC cos 2 pi fct. Real part of AC j c of at multiplied by it with a to the power j 2 pi fct is this. How do we get this equation? We have to just expand e to the power j theta as cos theta plus j sin theta using another formula. Then you multiply it and take the real part of this and you will get minus AC c of 80 sine 2 pi fct, right? Similarly, you can also take real part of minus AC CF square A square t by factorial 2 multiplied with e to the power j 2 pi fct, which is very simply, you can say it is minus AC. It is very clear, right? You replace it with cos theta plus j sin theta. You multiply this here and you take the real part, and the real part will be minus AC CF square by factorial 2 A square 2 by 2 cos 2 pi fct. So I can write my frequency modulated signal like this. You replace first term with AC cos 2 pi fct. The second term, this is the second term, real part of this. So the second term with this, minus AC c of 80 sine 2 pi fct. And third term with this. Excuse me. The third term with this. This is your third term. And there will be many terms, so just we write up to 3 terms. Now our aim was, if you remember, our aim was to analyze the bandwidth of this frequency modulated signal. So if we write our frequency modulated signal in this form, it is easier to analyze the frequency content of this signal. If you see this frequency modulated signal term by term, the first term is nothing but the carrier signal, and second term is carrier signal or sinusoidal signal multiplied with AT. So if you remember the DSBSC or the amplitude modulation, DSBSC amplitude modulation, the form of DSBSC modulation is AC MT cos 2 pi fct. What does it mean? It means if Fourier spectra of MT is like this, then DSBSC, the spectrum of DSBSC signal is shifted, frequency shifted version of this signal. So as you can see, for any DSBSC type signal, the signal component is centered around Fc and width is 2 FM, twice of the maximum frequency component of this signal MT. So if you see the first term, it is quite clear that this is a carrier signal. So there is no, this is DC only, right? Because there is no message signal, this is single tone. So all the content is available at Fc. There is no width of that spectrum. Now if you see here, the second term, okay, let's analyze the second term. The second term is minus ECC of AT sine 2 pi fct. So if you analyze the spectrum of this signal, whatever is the spectrum of AT, the spectrum of this whole signal is nothing but the shifted version of this signal. See this spectrum. So our aim is to derive the frequency component, frequency spectrum of this AT. And AT we have defined as, or we have represented by minus infinity to T mu du. If you remember from our very initial discussion, this, where we replace the integral of mu du with AT, right? So what is the spectrum of AF? If you see the Fourier transform of AT, it would be look like this. It would look like this, right? This is very simple, and you know it from your signal and system course. So bandwidth of this AT signal will be equal to bandwidth of your MT, right? So what can you write? If you can write the maximum frequency component of AT is same as the maximum frequency component of MT. So this is what we see from here, because it is nothing but integral of a signal MT. So integral, if you integrate it, the spectra, the width of the spectra remains same. So using this, we can say here that the width of this spectrum also will be same as the width of the MT signal or MF spectra. The shape would be changed, of course, because of this factor 1 upon j2 pi f, but the support or this width will be same. So the width of this signal or this signal will be centered around Fc and width will be Fm, right? Fc plus minus Fm. You just shift it, right? Because sinusoidal will shift it. Though, I mean, we are just taking the magnitude because we know that sinusoid also has this type of. So we are ignoring.
Hello, Ram sir.
Sorry for the inconvenience. So this is the. So what I'm saying that this part of the signal will also have frequency available around Fc and the width will be plus minus Fm. So total width will be 2Fm, right? Next we analyze third term. Third term is AC Cf square, A square by factorial 2 cos 2 pi Fct. So let's analyze the third term. So we want to know what is the maximum frequency component of A square T. So in order to analyze this, we write A square T as AT multiplied with AT. You can write A square T like this, right? And using the Fourier concept that product in time domain is convolution in frequency domain. So what is the Fourier frequency spectrum? Fourier transform of A square T is nothing but AF convolved with AF. And there is a property of convolution operation that if you convolve two signals with support minus A to A and with support minus B to B, the convolution of these two signals will give you a signal, a resulting signal will have support my A plus B, minus A plus B say from minus A plus B to A plus B. So this is the support of your convolved signal, convolved resulting convolved signal. So using this concept, we can say that maximum frequency component of A square T will be maximum frequency component of AT plus maximum frequency component of AT, that is 2F. So by using this logic, we can see that A square T is a signal whose frequency component is, maximum frequency component is 2Fm. So A square T, Fourier transform of A square T, the shape, we are not interested in shape, but the maximum frequency component is like this. So what is the third term? Third term of the frequency modulated signal was this. AC Cf square by 2 and cos of 2 pi Fct A square T. So frequency component of this is centered around 0 and the width is to minus 2Fm to 2Fm. So if we multiply it with cos 2 pi Fct, the resulting signal, this, the Fourier spectrum of this resulting signal will be the shifted version, right? It will shift to minus Fc and Fc, but the width will remain same, minus 2Fm to 2Fm. So we can say here that the spectrum of this will be centered around Fc and the support will be from Fc minus 2Fm to Fc plus 2Fm. So what we have seen here till now that the spectrum of FM signal, this was our FM signal, right? This signal is, the width of this support of this is 0 support of this is plus FM to minus FM. So total bandwidth is 2 FM, right? Support of this is from plus 2 FM to minus 2 FM. So total bandwidth of this term is 4 FM. Similarly, for the other arising terms, it will be 6 FM, etc. So by this, using this logic, we can say the spectrum of a signal would consist of a signal which is first is DC. The second term will have a bandwidth of 2 FM. The third term will have a bandwidth of 4 FM and 6 FM and so on. So since we know that FM signal, the FM signal has infinite terms, the bandwidth of the FM signal will be infinite. So as we discussed in our initial class that FM has two benefits, that it is immune to noise and it gives you that all the effect, I mean the non-linear effect of amplifier at the transmitter does not distort the message, that we know from our previous class. But the price we pay is in terms of bandwidth. The bandwidth of noise, the FM signal is quite large as compared to FM signal. So we know that these are the two benefits of FM as compared to AM, that it is more immune to noise as compared to AM. And in AM, we know that we modulate the amplitude of the carrier signal. And the non-linearity actually affect the envelope or amplitude of the modulated signal. So if we transmit our AM signal and then we use amplifier, the amplitude of this might be distorted because of the non-linearity. So the message signal will be distorted. But in FM, we modulate the frequency. The frequency is having the information, not the amplitude. So non-linearity of the amplifier does not affect the message signal. So next we study the generation of the frequency modulated signal. Thank you.